Look far enough into deep space, and you will find something genuinely strange happening all around us. Countless galaxies scattered endlessly in every direction, each one moving through the vastness of space. Pull back even further, and the true scale becomes almost impossible to comprehend. Billions upon billions of galaxies, each containing billions of individual stars, extending outward in every conceivable direction. But here is the genuinely strange part. Nearly every single one of these distant galaxies appears to be moving away from us, regardless of which direction we happen to look throughout the sky. This observation leads to one of the most fundamental conclusions in all of modern astronomy. The universe itself is expanding constantly and continuously in every direction simultaneously. Consider a single spiral galaxy rotating slowly through space, similar in structure to our own Milky Way, a seemingly ordinary object that actually reveals something extraordinary once properly studied. Compare that some galaxies position now versus billions of years in the future, and the difference becomes clear. Steadily increasing distance, constantly growing as space itself continues expanding around it. To understand how scientists first discovered this phenomena, we need to travel back nearly 100 years to an observatory where a single astronomer was about to change our understanding forever. That astronomer was Edwin Hubble, working during the 1920s with some of the most advanced telescope technology available at the time, carefully studying distant, faint smudges of light in the night sky. Using this powerful telescope, Hubble began systematically observing and cataloging distant galaxies, meticulously recording their positions, brightness, and other measurable characteristics night after night. Many of his observations were captured on photographic plates, physical glass slides that recorded faint light from galaxies located millions, sometimes billions of light years away from Earth. As Hubble analyzed this growing collection of data throughout the 1920s, he began noticing a strange, consistent pattern emerging across nearly every single galaxy he had carefully studied and measured. For each galaxy, Hubble was able to calculate two crucial pieces of information: exactly how far away it was located and exactly how fast it appeared to be moving relative to Earth. When he compared these two measurements directly against each other across his entire data set, an unmistakable pattern began emerging clearly from what had initially seemed like scattered, unrelated data points. The farther away a galaxy was located, the faster it appeared to be moving away from us, a direct, consistent relationship that held true across virtually every single galaxy he examined. This discovery became formally known as Hubble's law, and it remains one of the most foundational, important principles underlying our entire modern understanding of cosmology and the universe structure. To understand exactly how scientists measure a galaxy, the speed from such enormous distances, we need to examine something specific happening to the light itself as it travels across space. As a galaxy moves away from us, the light waves it emits become measurably stretched out, gradually shifting away from their original color toward longer, redder wavelengths as they travel toward Earth. Scientists call this specific phenomena redshift. a direct, measurable indicator that reveals exactly how fast and often how far away a particular galaxy actually is from our location. By comparing a galaxy's light spectrum against a known unshifted baseline, astronomers can precisely calculate the degree of friction present, translating that measurement directly into concrete velocity and distance figures. Apply this technique across the entire observable sky, and a clear pattern emerges. Immediately, most distant galaxies show significant redshift, definitively confirming they are indeed moving steadily away from us. From these combined measurements, scientists derive a single, crucial number known as the Hubble Constant, a value describing precisely how fast the universe itself is currently expanding. In relatively simple terms, this equation states that a galaxy's velocity equals the Hubble constant multiplied directly by its distance, the single foundational formula defining our universe's overall expansion rate. To actually determine these crucial numbers with real precision, scientists rely on two genuinely different measurement approaches, each examining completely different aspects and eras of our vast, expanding universe. The first approach focuses on the earliest possible moments of the universe's existence, while the second approach instead focuses on much more recent, relatively nearby cosmic objects and events. Let's begin with the first method, which involves peering back toward the very edge of observable time itself, examining light that has been traveling toward us since the universe's earliest moments. This ancient light is known as the cosmic microwave background, essentially the faint leftover radiation released shortly after the Big Bang itself, still detectable today, filling the entire observable universe. Missions like the Planck satellite have mapped this ancient radiation in extraordinary detail, capturing incredibly precise measurements of subtle temperature variations spread evenly across the entire visible sky. This particular light originated from an incredibly early moment in cosmic history, when the universe itself was merely 380,000 years old, astonishingly young by cosmic standards. Now let's examine the completely different second method, which instead focuses on specific, well-understood stars located within relatively nearby galaxies throughout our local region of the universe. Scientists rely heavily on a particular category of star, known as Cepheid variables, stars whose brightness rhythmically pulses in a precise, predictable, and extremely well-understood pattern over time. Alongside these pulsing stars, scientists also study a specific type of stellar explosion known as type La Supernova, events whose peak brightness remains remarkably consistent and predictable across different occurrences. Astronomers refer to both of these objects types collectively as standard candles, since their non-predictable brightness allows precise distance calculation based purely on how dim they actually appear from Earth. By carefully measuring exactly how faint these objects appear from our vantage point, scientists can calculate remarkably precise distances and subsequently an independent measurement of the universe's current expansion rate. In theory, both of these completely independent measurement methods should ultimately produce the exact same final number for the Hubble constant, since they are both measuring the same underlying physical phenomena. But when scientists actually compare their final results side by side, something genuinely unexpected happens. The two numbers consistently refuse to match, despite repeated careful measurement attempts. This is not simple measurement error or minor rounding discrepancy either. These two numbers should theoretically align perfectly, and yet they simply don't, no matter how carefully the data is analyzed. As more research groups continued publishing their own independent results, a clear pattern began forming: measurements consistently clustering into two separate, statistically distinct groups rather than converging toward one shared number. Scientists have given this persistent, unresolved discrepancy a specific name: the Hubble Tension, a genuine ongoing puzzle that continues challenging some of our most fundamental assumptions about cosmology. For physicists and cosmologists working directly on this problem, the implications extend far beyond simply determining one specific number describing the universe's overall expansion rate. If two completely valid, independently verified measurement methods genuinely disagree consistently, it strongly suggests our current understanding of the universe might be missing something significant and currently unexplained. This possibility has generated enormous scientific interest and considerable ongoing debate, with researchers actively proposing several genuinely different explanations attempting to account for this persistent, omniscient discrepancy. One leading theory suggests the answer might lie within dark energy itself, the mysterious, poorly understood force believed to be actively driving the universe's ongoing, accelerating expansion. Perhaps dark energy behaves differently across cosmic time than our current models assume, potentially explaining why measurements from the early universe don't perfectly match measurements taken from more recent nearby objects. A second competing theory proposes the existence of entirely new, currently undiscovered particles that may have existed briefly during the universe's earliest moments, subtly influencing our current calculation and measurements. If such particles genuinely existed during this critical early period, they could have measurably affected the cosmic microwave background, potentially explaining part of this ongoing measurement discrepancy scientists continue observing. A third, more fundamental possibility suggests something deeper might be wrong entirely, that our current standard cosmological model itself may require a significant revision or meaningful updating altogether. This particular possibility remains genuinely controversial within the scientific community, since our existing cosmological model has successfully explained an enormous range of other observed astronomical phenomena remarkably well. Fortunately, new tools are actively helping scientists investigate this ongoing mystery further. The James Webb Space Telescope, launched specifically to observe deep space with unprecedented clarity and precision, has already begun contributing. Using James Webb's significantly improved observational capabilities, researchers have already obtained new, more precise measurements of distant CP variable stars, helping refine and double-check previous calculation and results. Beyond James Webb, several additional future missions are currently being carefully designed and planned specifically to help resolve this persistent tension once and for all, one way or another. Whether these upcoming missions ultimately close this frustrating gap entirely, or instead definitively confirm that it's genuinely real, the ongoing search for a clear, satisfying answer continues actively today. Regardless of which exact number eventually proves correct, one fundamental fact remains completely unchanged throughout this entire, ongoing scientific debate: our universe is expanding continuously and measurably every single moment. Not only is it expanding, but current evidence strongly suggests this expansion is actually accelerating over time, with galaxies moving apart from each other increasingly faster as cosmic time continues progressing. Scientists attribute this puzzling acceleration to dark energy, a mysterious, poorly understood force that appears to be actively pushing the entire universe apart at a continuously increasing rate. Despite decades of dedicated research and increasingly sophisticated observational technology, dark energy itself remains one of the largest, most significant unsolved mysteries in all of modern physics and cosmology. Consider our own small, relatively insignificant position within this unimaginable, vast, constantly expanding universe, a single planet orbiting a single star among countless billions of other stars and galaxies. Somewhere out there, across this vast cosmic distance, galaxies continue pulling steadily away from each other every single second. Driven by forces scientists are still actively working to fully understand. The precise number describing exactly how fast this is genuinely happening remains, for now, a genuinely unresolved scientific mystery, one that could potentially reshape our fundamental understanding of physics itself. If this mystery genuinely fascinated you, then subscribe, because there is an entire universe full of unanswered questions still waiting out there, and we are covering them one video at a time. Thank you for watching.